It's my pleasure to introduce today's Lauren lecture speaker. It's our own Lauren Linderman. Lauren got her PhD from Illinois in 2013 and then directly came to the University of Minnesota, where she's been an assistant professor since. Some of Lauren's bigger achievements are she was the 2018 Rosine Anderlich Teaching Award winner. In 2018, she also got an NSF Career Award. And in 2019, she won the ASCE Minnesota Young Engineer Year Award. And with that, I would like to turn the tables over to Lauren and have her talk to us about network wireless control.
Thank you, Carol, for that kind introduction. Today I'm going to talk about my group's work specifically related to wireless control systems and how we address these network challenges that come up when we're doing structural control. And so I'll start my talk today even giving some intro on why do structural control and what it is, and then what specific challenges does wireless pose, and then what are 3 ways that we can address these challenges to come up with better performing systems that are kind of unique and interesting. And so I'll talk about decentralized control, sensor selection, and then an analysis approach that we can use to assess our design parameters. And then finally, some conclusions. So there's natural hazards around. So we have wind, earthquake, even human-induced vibration, although that's not a natural hazard, can also cause large motions. And when these are applied to structures, typically we try and dissipate that energy through damage. Okay? So we try and make sure our structures are safe for life safety, but they may undergo significant damage and not be usable after an event. Okay. So recently there's been a switch towards low damage design, and so we would like to have less damage after an event so that we can actually use the structure again. And one way to do this, rather than just pure structural modification, is to use structural control. And so structural control offers an alternative for reducing the building response. And there's several ways that we actually implement structural control systems. Probably the most common is passive. And so when we introduce structural control, we're trying to limit our vibration response by altering the mass, stiffness, or damping of our structure, or introducing counterforces. And sometimes we do this by incorporating a supplemental damping device. In passive control systems, we're actually responding to the motion of the structure itself. We're not inputting any energy into the system. And 3 common ways we do this are base isolation system, where you actually have the ground isolated from the structure so they can move relative to each other. You also have passive dampers, which you can think of as a large viscous damper, similar to shock absorbers in a bike. Okay. And probably the most famous passive system is the tune mass damper in Taipei 101. It's a very large pendulum that is designed to vibrate at the natural frequency of the building. And so when the structure vibrates, that damper actually sucks up a lot of the energy rather than the building vibrating significantly. Now, one challenge of passive control approaches is they're typically tuned for a very specific type of input motion, and they're also sensitive to detuning in the structure. So one way we can handle this is to use feedback. And so we actually put sensors throughout our structure which take information or measurements about our system, and this feeds back into a controller that makes a decision about what we want to do. And often we'll apply some sort of counter force device to limit the motion. And these are typically applicable over a much broader frequency range of excitation, so we can have a much larger variety of input forcing that we're trying to control. We can also tailor our control design objectives depending on the amplitude of the motion. But one challenge with these is they have this feedback loop. And in active systems, we're actually putting energy into the system, so you can go unstable. So we're taking a stable system, so my building should be stable, and we have the potential to make it unstable as a trade-off for good performance. Another approach we could use is semi-active control, And so in that type of system, you're changing the properties of a passive device in real time. So what does that mean? Let's say I have a viscous damper. That's a passive device. It's just taking energy out of the system through damping. I could change the properties of that viscous fluid in real time. Okay? So I could make it more or less viscous. So these systems don't actually input any energy into the system. So today I'm going to focus on active and semi-active control systems using feedback structural control. Now, why would we make this wireless? Okay, so most structural control systems are tethered. Wireless sensors originally gained significance, at least in civil systems, through monitoring approaches. And the idea is that we could use these wireless systems for structural control. The reason we would want to do that is these systems typically have onboard computing and sensing properties, so we can have distributed sensing and computation throughout our structure. Okay? They also offer, by having this distributed nature, we can adjust our control system to respond to sensor or controller failure. So if we have a sensor that fails, we could rearrange our network system, or if we have a controller that fails, we're not stuck with one tethered controller. Okay? It also limits the cabling requirements by having wireless systems in there. And also by having this distribution, it encourages novel feedback architectures that haven't been explored in civil structures before. And so they can offer some pretty unique advantages. So while I've touched a lot on why wireless control is great, applying some of these wireless systems to control poses challenges because now we're dealing with really real-time phenomena. So when you use wireless sensors for monitoring, that's typically a slow, long event. I'm not worried about real-time behavior. When I start to use them for control, I want to know what's happening in the structure right away. Okay? And that poses some challenges. So the first one I want to talk about is timing. Okay? So each sensor has kind of its own independent clock or its own independent processor. And so you can think of this as having its own independent brain. Okay? And the best way that I like to show this is that when I snap my fingers, I'm going to ask all of you to raise your hand. Okay? Cool. So all of you did it at a slightly different time. Okay? And some of you didn't do it at all. So you would be a dead node. Okay? And so you all did it at slightly different times, so you all have slightly different reaction time. And you can think of that as you might have something else on your mind. Okay? Maybe you're hungry, maybe you're bored. And so you all do it at a slightly different rate. Okay? So each sensor has its own processor, and it will do things at a slightly different time. And so what does that lead to? It leads to uncertainty in timing, particularly for data acquisition, applying control commands, or communication between nodes. So for example, if I'm trying to sample the same signal with a bunch of different sensors, I might actually see a slightly different signal. That's one possibility of how this would impact our structure. Another issue is wireless data transfer. So you're probably all aware that wireless signals can drop out, okay? I mean, you can lose data. And so what we're worried about is, let's say I have a lot of local sensors that are trying to communicate with my controller, okay? And they all communicate at the same time. They're going to interfere with each other, okay? And this interference is going to cause two main issues. It's going to cause data loss, okay? Because they're communicating at the same time, so it will increase the inherent unreliability, okay? And it can also cause communication latency. So these sensors don't like to communicate at the same time because it causes data loss. And so they'll typically have a random wait time before they send. And this can cause a non-deterministic delay between when you tell them to send and when they actually do. Okay? So there's different ways we can handle this to try and tune the relative data loss versus latency. One really common way to do this is to have them send on a scheduled approach. So each sensor sends at its own slot, okay? so that you're less likely to have interference, and you also have a known time between when I take a sample and when it'll actually be received at the controller. Okay? Now, what you can tell is that took me a lot longer to do. Okay? And so as I increase the number of sensors, the delay between when I take the data and when the controller can actually process it increases. Okay? So this limits the sampling performance of our controller, because it's only going to respond once it receives all the data. Okay? Now, why does that matter? Structural systems typically respond at a relatively high frequency. And so let's say my structure is responding at 6 hertz. Okay? And then I sample that signal at 10 hertz. Okay? So I can't see that 6 hertz signal anymore. I'm seeing a 4 hertz signal. Okay? I can't recover that original signal. This is called aliasing. Okay? So if I want to recover and be able to see that 6 hertz signal, I would at least need to sample twice as fast. If I want to control that signal or that response, typically I want to sample 10 to 20 times faster. Okay? And so for a 6 hertz signal, I would want to be running my control system at least 60 hertz. And this can be challenging when you're trying to communicate a lot of information back to a single control node. So the 3 key challenges that I want to talk about today are timing, latency or sampling rate, or large sampling rates, and then data loss. Okay? And there's 3 main ways that we can address these challenges. So we can use a hardware or middleware-based solution. And so here we would actually control our hardware or our software to maintain tight timing. Okay? And so we can limit our packet loss or have a clear sampling rate of our system. By packet loss, I mean data loss. Or we can even tailor our communication protocol to achieve a certain data loss or latency in our system. There's also non-hardware-based approaches. And so the 2 main ones I want to talk about today are our feedback architecture. So how is my controller using its sensor measurements? What measurements are actually feeding back to the controller? And to do that, I would like to look at decentralized control approaches. So I limit the amount of information that's required. And I can also have controllers distributed throughout my structure. The other thing is to actually select where my sensors are going to be located to limit the measurements feeding back into my system, which should limit the sampling delay. Okay? And then finally, I'll look at how do we actually model these control designs, okay, for doing analysis. So civil systems are very large. They have large model uncertainty. And so typically we'd like to have a good idea of the performance over a range of inputs, and in this case, a range of data loss scenarios. And so how do we come up with an analysis technique that can give us insight into the performance? So we're going to use what's called jump system models to model the loss process, so the data loss in our system. This will also allow us to consider different controller designs as well. And so today I'm going to focus on these 2 main topics that we've worked on in my group, and then tailor them to how they impact the performance of our control. So the first one I'm going to talk about is decentralized control. So we're limiting the feedback that our controller needs to make its decision. So let's say I have a structure that's excited by the ground, okay? And it has sensors distributed throughout. And right now, I'm going to assume those sensors can measure the states of my system. And by states, I mean displacement and velocity. They can mean other things as well, but that's a really common way to think about the states. Okay? The information about this displacement and velocity is going to feed back into my controller, which is going to determine the control gain or control forces it would like to apply. And we're going to use a control law that just uses a gain matrix that multiplies my displacement and velocity. And typically, this gain is designed to limit the variance of the displacement and the velocity of my structure. Okay? And so our objective here is to limit the number of states I need to feed back into this system, okay? So this would be a purely centralized system where all the states are coming back into my controller, okay? There are other approaches. I have a fully decentralized approach where my controllers only have local knowledge. They're not talking to each other. One way to think about this is, let's say this story has its own controller. It will only know information about its own story's response. So it will only know what's happening at the second story. It won't know what's happening at the first and the third. So I'll have controllers distributed throughout, but they only have local information. Another way of doing this is a partially decentralized approach. So there's some information sharing, so I have more knowledge about the global behavior of my system. So for example, if I have a controller at the second story, it might know what's happening at the first story and the third story. Okay, that's one example of a partially decentralized system. Now the challenge is, how do I design these such that I still get good performance? So let's say I have a 3-story structure, and I have a controller at each story, and my states are going to be the displacement and the velocity of each story. I'm going to multiply those states with my gain matrix to compute my 3 control commands at each story. Okay? And so this gain matrix is this K here. And again, this is designed to limit the variance or the RMS response of my structure. Now, if I have a system like this where my controllers and my sensors are located at the same location, so it's co-located, typically my gain matrix is going to have really large values on the diagonal. Okay? So one way to manage this is to design a decentralized system is to just use an ad hoc approach. And so I'm only going to keep the large values, and I'm going to zero everything else out. This is a pretty crude way to do it. It's definitely suboptimal, but it can be pretty effective. Another way to do it is to actually enforce a sparsity pattern when I design the control gain. So before, we assumed we're designing a centralized controller where I have all the state information about my structure, and we just brute force cut things that didn't apply. Okay? In this case, we're actually going to make sure that my controller only puts values for, say, at the diagonal. Okay? To do this type of control design requires a heuristic or an iterative approach. And because of that, we're highly sensitive to the starting value that we use to actually design the control gain. And so you can have relatively suboptimal performance depending on where you start your actual design. So what we're looking for is a more systematic way of doing this. Okay? So we've applied a method using optimal sparse control design to civil structures. What this allows us to do is incorporate the sparsity, and by sparsity I mean limit the number of states we need in our controller, into our overall objective function that we use to design the control gain. Okay. So what I have here is I want to minimize the closed loop RMS response of my structure. This is the typical cost function that we would use to design our controller. Okay? So this is our standard approach. And what we're doing here is we're adding in another term. So we're adding a term that weights the sparsity of the gain matrix. Okay? So a common way to do that is to do the cardinality of the matrix. All that means is the number of non-zero values in the matrix. So for example, for that previous heuristic design, I only had values on the diagonal, which means the cardinality of that would be 6. Okay? You can also do, this is a really hard thing to optimize because it's a really harsh constraint. Okay? You can relax this to have something that is more convex. Okay? And use an L1 norm. So basically we're just summing up the absolute values of all the elements in the matrix. And then we weight the relative importance of the response and the sparsity with a weighting parameter. Okay? And my weighting parameter gamma If it's 0, I get back the original centralized system. As gamma increases, I should have a sparser and sparser gain matrix. Okay, so less feedback required, while still trying to achieve good performance. Now, what are the advantages of this? I don't have to make any assumptions about the structure of my gain matrix ahead of time, okay? And this can be particularly effective for civil structures because often my model is not a true physical representation of my structure, but just represents the input-output behavior, okay? And so if I don't really know what my states mean physically, it's hard for me to figure out what to actually cut. Okay? It also allows me to clearly balance the number of feedback states that I need and the performance, and I can clearly identify which states are most important because it's going to give me a whole suite of gain matrices. And then finally, if I am doing a structured problem at the end, so I have my form of my gain matrix and I want to refine it, this initial guess is going to be much better than what we typically use in a heuristic approach. And so we have applied this to a 5-story structure. Okay? This is based off of a real structure in Japan. It's the Kajima Shizuoka building. It's a 5-story steel structure fitted with semi-active hydraulic dampers at each story. And in this case, we're assuming that we can measure the displacement and velocity of each floor. Okay? And our goal of our controller is to limit the inter-story drifts of each floor. So we'd like to limit the relative displacement of each story because that is what leads to damage. So it leads to damage in the facade and things that make this structure usable. So we applied our approach to this system. So let me explain what you're seeing here. On the left is you see all the different patterns in the gain matrix as we increase the weight on sparsity. Okay? So the original gain matrix will have 50 elements. It would be fully populated. Okay? So I have 5 control feedbacks, 5 displacement states, and 5 velocity states. So I have a 5 by 10 matrix. Okay? And as I increase the sparsity, the number of non-zero elements should go down. Okay? What you see on the left is the number of non-zero elements as I increase my weighting parameter. Okay? And the corresponding difference in the performance from the original centralized system. So as I increase the sparsity, I get worse performance. Okay? So what the advantage of this approach is that I can see whether there's clear changes in the performance as I drop elements from the gain matrix. So when I no longer need certain states. And so you can see that I don't actually change my performance that much and still lose quite a few components. Okay? And so those are states that either I wouldn't need to measure, so displacements or velocities I wouldn't need to measure, or states that I wouldn't need to estimate. Okay? And I want to focus on 2 feedback gain matrices. Okay? The first one is where I have 18 non-zero elements. You can think of this as a partially decentralized system. So my stories would need information from the neighboring stories when they compute their control command. Okay? And then I have a fully decentralized system down here where I'm only taking local information, so I only need the displacement and velocity of that story to make a decision. So what you'll notice is this looks a lot like the heuristic form that we imposed before. I do want to compare the difference in the final cost or performance of the system using the 2 approaches. So the heuristic performs significantly worse in the design than our optimization approach. And so to test this out, we applied this to our structure subjected to 4 common earthquakes or historical earthquakes. So we have El Centro, Northridge, Chichi, and Kobe. Okay. What you see on the top is the maximum drift at each story. Okay. And what you see below is the maximum force required to obtain that performance. Okay. The blue line all the way to the side, this is the uncontrolled system. Okay? So clearly we have more drift there than we do on the others. Okay? The black is LQR, so this is the fully centralized approach. The green is going to be our partially decentralized approach, and the red is our fully decentralized approach. What you can see is, despite having limited information, I still have really good performance. Okay. The purple diamond that we're comparing it to is the heuristic design. Okay. And you see here it also has pretty good performance. The biggest difference that we see is the force required to achieve that. Okay. So for our decentralized and partially decentralized, we have a much more even distribution of force along the height of the structure, which should make it easier to design, and we have lower forces on average. So in all of these cases, I'm trying to limit the actual states that I'm feeding back, and so we find that despite having limited information, we can still get pretty good performance in this case. Now, it's actually really hard to measure the states of a system, okay? So it's really hard to measure displacement and velocity of a structure. It's a lot easier to measure acceleration, okay? Also, a lot of times our states, again, may not have physical meaning, and so I need to use what's called an estimator, okay? And so now what I want to look at is what sensors do I actually want to use if I'm using a limited set of measurements to estimate my system response. So often we'll have accelerometers on our structure, and we're going to use this with an estimator based on the model of my system to figure out what the states are, so what the displacement and velocity response of my structure is. So I'm measuring acceleration, and then I actually need displacement and velocity to compute the control. Okay? So all we've added in here is an estimator. That's what makes this different from the previous problem. And so what we'd like to do is minimize the number of sensors we need to use while still getting a good estimate of our states. Okay? And so by doing that, what I'm going to say is we need small error in the estimate. Okay? Now, what this sounds a lot like is choose M from N. Okay? So we'd like to choose M sensors out of N possible locations. This is a combinatorial problem. So for example, if I want to place 3 sensors out of 9 possible locations, that's 84 different combinations I would want to consider to figure out which one is the best to minimize the error. Okay? So what you can imagine is civil structures can be really large scale, and so this can be significantly challenging as the scale of the structure increases. Sensors will drop down, and correspondingly, our estimation error is going to go up. Okay? So originally, we had our 4 measurements, so an accelerometer at all 3 stories and the device at the top. The initial cut it makes is to get rid of measurements at the 2nd and 3rd story, and only retain measurements at the 1st and at the device. So you can think of this as the 1st story and the top of the structure. Okay? As I continue to increase the sparsity, I end up with only needing the measurement at the 1st story. This was originally counterintuitive to us because we thought you would have the most motion at the top of the structure, and so that's what you would want to measure. In this case, we thought we had a slightly uncertain model, okay? And so this input gives us information about both the input into the structure, so the excitation that's going into the structure, as well as its motion. So by having a sensor at the 1st story, we're closest to the excitation. So we have some information about what's actually exciting my structure. And so we apply this to various different earthquakes again, okay? And so we would like to compare the control performance. And so what I'm showing here are the 1st story and the 2nd story displacements to our structure when excited by the Kobe earthquake. The red line is the uncontrolled. The blue line is when we have all the sensors feeding back. And the green line is the sparse system. So we only have one accelerometer giving us information about what's happening. What that allows us us to do is run a lot faster. So we don't have as much delay for the measurements to get back to the controller. And what you'll notice is that despite having less information about the structure, that speed of being able to respond actually offers us pretty good performance. And so we're typically comparable to the full feedback system, so when we had all measurements. Now, some of you might ask, well, I'm running all of these through individual simulations, okay? What does this have to do with real structure design, okay? So when I design a structure, I'd like to have information about all the different types of inputs I might have to my system, what impact that would have on the performance. There's going to be all sorts of data loss scenarios that are going to occur in these types of systems. And so in control design, in the controls community, you often use a mathematical analysis or a norm analysis to evaluate the performance of my controller over a wide variety of system designs and inputs. And so what we'd like to do is leverage that and tailor it for these types of systems where we have data loss and latency. And so what this allows us to do is do a clear analysis of what design parameters affect our system, and also we can use these models to improve the design of our controller. Okay? So our goal is to quantify the impact of data loss, sampling rate, and our control approach on the closed loop performance. And so when I'm talking about the closed loop performance, typically we'd like to minimize the inner story drift of our structure. Okay? And so if I look back at our original closed loop system, I'm going to model my wireless network just with two parameters, the sampling rate of the system and the data loss probability. Okay? And then my controller, I'm going to look at different controller designs and also how my controller manages signal loss. So what does it do if it actually loses data? Okay? And what impact does that have on the performance? So if I have a linear time invariant system, doing an analysis like this is pretty simple. But now with these parameters, we're no longer time invariant. So our system is changing with time because we can receive data or lose data. Okay? So we're now jumping between two different systems. And so we needed to tailor the typical analysis to use with this more complicated model. So the way we did this is we modeled our wireless structural control system, and then we did an analysis of the closed loop performance. And the key components of our model were to use a sample data system. So our controller is operating at a slow rate, okay? But our structure is responding in real time, okay? So it's responding in the continuous time domain. And what I'd like to be able to do is capture the response of the structure in between each time I apply a control force. And so to do that mixing of the two different rates that are in my system, we use a sample data system. We also wanted to account for the data loss, or the probability of data loss. And so what you can think about is we're jumping between two different systems. I have a system where I've received all my data, and I have a system where I've lost all my data. Okay? And we simplified to model this as a Markov jump system. So we're jumping between two systems with a certain probability. And to simplify this, we assume that we either receive all of our data or we lose all of our data. And that is a simplification. Okay? And this type of system is just a Bernoulli process. So we're losing a sample with probability p, and we'll receive it with probability 1 minus p. Okay? And then we looked at how our controller design can handle data loss when we model it. So let's say I lose data, okay? I have two kind of main options. One, do nothing, because I don't know what's going on in my structure. So I actually apply no control, okay? Another option is that I can hold whatever control I had before until I get more information, okay? So those are two main ways that I can manage data loss. And then also I have two different types of systems that we've looked at here. I have a control design where I assume I can measure my states, okay? I also have a control design where I'm taking a limited number of measurements and estimating the states. Okay? And so we solved this combo of systems using Lyapunov equations, which are then solved with algebraic Riccati equations. What this allows us to do is actually calculate the performance over a range of data loss scenarios. Okay? So if I lose data, that might happen at different times for different excitations. So I may not always lose the third sample, I might lose the second sample. Or I might lose multiple samples in a row. And so what I'd like to do is have some insight on the impact of all those different data loss scenarios on the overall performance of my structure. So we apply this to the 3-story SAC benchmark model. There are a series of steel structures designed for the seismic requirements in LA. Okay? Low height structure, a mid-height structure, and a tall structure. Here we're focusing on just the 3-story structure. Okay? So while it was never built, it's a real design. Okay? Our control system parameters, we're looking at 2 main sampling rates here, 20 hertz and 50 hertz. So our 50 hertz signal is, our 50 hertz controller should be able to control even the third mode of our structure. Okay? We're also assuming 2 different control designs. The first is I'm assuming I can measure all my displacements and velocities. And then when I compute my control command, I either do nothing if I don't have data, okay? Or if I do have data, I just hold what I had before. The other is to actually use an estimator where we have our acceleration measurements and we're estimating our states. And we compared our analysis approach to simulations to see how good our analysis is at capturing some of this behavior. Okay. So what I'm showing here is I have my 3-story structure, I'm measuring the displacement and velocity of my system, and then computing my control command. And this is happening at some sampling rate, and then there's some probability of packet loss or data loss. If I have no probability of data loss, I have my perfect system. So I'm getting all of the information, no problem. Okay? If I have a probability of data loss of 1, I'm getting no data, and so I'm the uncontrolled system. I'm doing nothing. Okay? And so between that, I'm varying between a fully perfect system and an uncontrolled. Okay? What I'm plotting here is the mean of the RMS interstory drift. So you can think each data loss scenario is going to cause some overall closed loop performance. Okay? And what this analysis does is it takes the mean of all of those different variances. And what I'm comparing here is a system where if I lose data, I just hold my previous command until I get more information. Okay? What you'll notice is here I have 2 different sampling rates. The red is I'm operating at 50 hertz. The solid line is I'm operating at 50 hertz. The dashed line I'm operating at 20 hertz. Okay? So the 50 hertz system gives me better performance, so I don't actually have that much worse performance up to about 70% packet loss. But then I actually become worse than the uncontrolled system. So I'm worse than doing nothing. Okay? So I could have better performance using this type of approach, but I do run the risk of not being robust to high levels of data loss. Okay? What you'll also notice is that the slower controller has slightly less effective performance at these higher packet levels, but I'm a little bit more robust to higher data loss. Okay? Now, I typically don't want to use a system that's going to be worse than uncontrolled, that's worse than doing nothing. And so when I'm designing my system, I would need to be really cognizant of whether I can actually achieve a wireless system that won't have that level of data loss. Okay? Now, what happens if I manage data loss differently? Okay? So before we looked at an approach where if I lose a sample indicated by the circle, I just hold that command until I get new information. I can also turn my system off when I lose information, and then when I gain information, actually apply a new control command. Okay? So what you'll see is this type of approach gives me less effective performance at lower levels of packet loss, so it just monotonically degrades with increased packet loss, but I don't have any chance of going worse than uncontrolled. Okay? So my performance will degrade, but I never need to be concerned about it being worse than doing nothing. Okay? What you'll also notice is that the response is very similar for the two different sampling rates. Okay? So this gives us some insight when we're designing of whether we're willing to sacrifice some performance to be robust to a variety of networks. Okay? Now, we compared this with simulations just to see how accurate or effective is this analysis tool, because it's a much easier way to evaluate different design decisions for a variety of inputs. And so what we show here are those two different control approaches operating at 50 hertz. Okay? So, below 80% probability of packet loss, these basically have very small variance in the simulations relative to the analysis. So the mean of the analysis should lie on the solid line, or the mean of the simulation should lie on the solid line of the analysis. So each of these is a mean and variance of the simulation. So we're considering different scenarios of packet loss and figuring out what the variance of the response is. So what you'll notice is that for this on-off approach, the variance does increase as I increase my data loss. So that increases slightly, but overall this gives a pretty good window on what's happening in the system. But for the system where I have a really large change in performance, the variance becomes very large, and the mean is often below our analysis curve. And what we find is that this will indicate there's going to be some large change in behavior, but it might not give the full bounds of the performance. Okay, so I could actually be much worse than the analysis predicts. Because as you get much higher data loss, we have a much higher variance in the system performance. Now, what happens if we change our controller? Okay, so before we're assuming we can measure our states, what happens when we add an estimator in there? And to me, this really shows the power of an analysis tool, rather than running lots of different simulations, which is what we typically do in structural control design. So what I'm showing here is, again, the variance of the inner story drift as a function of the probability of data loss. So again, if data loss is 0, I get back all of the information. As data loss is 1, I have the uncontrolled system. Okay? I'm showing a system here where we have an estimator taking measurements and then computing a control command. And what you see here is that my system that's running faster, so my system that's running at 50 hertz, actually goes unstable. And so this was a really surprising result because our system should always be stable. So if I have my control design, that's a stable design. Okay? If I have my estimator, that's a stable design. And so it's surprising that bouncing between two stable systems, I can actually become unstable. Okay? So normally when we do control design, we assume that we're designing a stable system. Okay? And so this is pretty concerning. And what's also interesting is that with simulation, I might have some instances where the response is stable depending on how the data loss occurs. And I wouldn't be able to observe the instability using just simulation. Okay? But when I respond at a slower rate, so if I'm only running at 20 hertz, we actually remain stable the entire time, and our performance degrades monotonically. Okay? And so we can use this type of analysis to quantify the behavior under different design decisions. We'd also like to extend this to use for actually designing the controller and incorporating in some reliability analysis where we're actually calculating the probability of failure of a controlled system. So in summary today, I've looked at 3 non-hardware based approaches to address the challenges of wireless control such that we can tackle some of these in a creative way. And so the first 2 are really to limit the sampling time of my system. So we're using decentralized control and sensor selection. And we're using an approach that allows us to balance performance and system knowledge and give us a really systematic way of designing our control gain. We also looked at an analysis approach that allows us to evaluate these design choices, particularly the range of acceptable data loss that we're willing to accept in our design, the sampling time that we'd like to use, as well as what controller implementations are more effective. Okay? And so we're extending some of these. We're extending this towards probabilistic design and reliability of our systems. And we're extending our sensor selection approach to consider different measurement types, as well as using it for monitoring systems where we have really large-scale structures. So I'd like to acknowledge my group here that did most of this work, particularly Kaylee Gustafson, Tao Trong, and Ruben Brodoliak, as well as my collaborators, Mihailo Jovanovic, who is now at USC, and Pete Seiler in the aerospace department, as well as support both here from the university and department and the NSF. So thank you for your attention.
Thanks, Lauren, for a great talk. I think we have time for a few questions. Randy.
Questions of latency come up in things like online gaming. And one of the solutions that they take is have a canonical model that predicts what's happening and then only send packets if it's not what they predicted. It seems to me that that approach would be applicable here in that as you design your building, you can actually make reasonable predictive models. Wouldn't that improve the problems with latency?
So there have been some investigations of where you propagate your estimate forward using your model, and then if it's widely different, then you actually send data. The challenge there is you're going to have a varying sampling rate as you move through your system, so it's a slightly more complicated design. Typically, we like to avoid time-varying designs in structural control because they pose a lot more challenges of implementation. Could be a really effective approach. I've seen a few examples of it being applied, and I haven't seen significant improvement. I think some of that is the model can vary as well, and so your prediction is highly dependent on the level of excitation and also how your model is changing. But it is a potential way to do this as well. That answers your question.
Other questions?
What is the best method out there right now that's actually deployed? In other words, what's the gold standard that you're trying to improve upon?
So wireless control has not been deployed yet. That's because our industry is relatively risk averse. So for civil systems, it hasn't been deployed. So that is one reason we'd like to look at the probability of failure, because that fits into the design framework that structural engineers actually use. For structural control systems that have been implemented, the gold standard right now is passive, and there are some systems that use, or some structures that use active control. Typically they are hybrid systems, so you have some active control with a passive device. Those have been shown to be really effective, but they're typically only in countries that really are worried about this, so Japan, where they're encouraging some of these new deployments. But it is not widely used in overall structural design, as much as you'd see in other fields. And I think part of the reason is that our structures are unique. So every single structure is different and would require its own unique design. And it's really hard to test the performance because you don't want to test it on a real structure. So I think that's some of the challenge to getting this adopted in industry. But I'm hoping that by coming up with these robust analysis methods, you might be able to encourage adoption.
Tuned mass dampers have been around a long time on buildings.
Yes, they have. And what I think is kind of interesting is base isolation, which seems like a pretty straightforward concept, took about 80 years to be adopted in structures. So there can be a pretty large lag between when something is invented and when we actually are confident enough to deploy it.
Wasn't MTS Systems locally one of the first deployers of the technology? In a building in Boston, I think it was in the 70s.
For
Tuned mass damper.
to be honest, I'm not.
Yeah, MTS Systems down at Eden Prairie was doing this a long time ago.
Yes, I know MTS is a leader in the field of designing control systems and also actuators, but to be honest, I don't know the first system that was used. I know the first active mass driver system in Japan.
I have a different type of question. When you were trying to impose a sparsity on the gain matrix, you showed the L1 norm. So are you vectorizing the whole matrix and then impose the L1 norm, or you are minimizing the nuclear norm? Because to my understanding, you are trying to impose a low rank representation of the matrix to focus on the diagonal elements. So what kind of norm are you using to impose the sparsity? Nuclear norm or vectorizing the whole matrix and imposing the sum of absolute values?
We're vectorizing the matrix. There's additional relaxations, which I didn't present for clarity, where we do a weighted L1 norm, which becomes closer to actual cardinality, where you inverse the value as your weight, basically.
I was curious that because if you vectorize and just minimize it, what guarantees that you get the diagonal? But nuclear norm, which is the sum of the singular values, if you minimize it, it imposes the low rank representation for that, and you will get the diagonal non-zero values. That's kind of...
So there's different ways in which we can weight the L1 norms. So if you just purely vectorize, I agree with you, you may not get the diagonals, and we have seen that. You can, if you know your co-location, enforce that those have higher weight because I have those right there. And so why would I not use them?
I'm curious if you would know what the controls are in the towers of the Kobe Bridge.
I believe those are hybrid mass dampers, but don't quote me on that. So I believe that is a tuned mass damper system where they can tune the period in real time.
I think we have time maybe for one more question.
It's not surprising that you're losing the performance when you increase the duration of the data loss. So if you freeze your control, you're kind of assuming that your structure is fine, but it actually keeps flying. If you try using this simplified rigid body dynamics model, to say, okay, during this loss, my structure keeps flying, and to account for that. Of course, you don't have time to do the full simulation since you have the initial condition, but at least something very simplified and the local.
Yeah, so that's interesting. We have not considered that. I think that could be a really effective approach, and particularly for estimation. And so sometimes you can even change your estimator from a predefined set based on your assumed duration of data loss. And so we've looked at that as well. And that can be a really effective tool to basically become almost as if you're time varying.
I think we're out of time for questions, so let's thank Lauren.